So now let's consider the time complexity of the elementary arithmetic operations: addition, subtraction, multiplication, and division. We'll start with addition since we'll need its time complexity for all the others. So the first question we need to address is, what is the input size? Clearly the addition will require fewer steps than the addition, so the obvious choice for the input size is the value of the addends. But this would mean that 1 plus 1 takes fewer steps than 9 plus 9, so the input should really be the number of digits. Now the number of digits in a whole number n can be computed using the ceiling of log of n. However, it will be convenient to let the number of digits be n and, if necessary, determine the time complexity based on the actual addends. Since the input size is the number of digits, then our basic step should be the addition of two single-digit numbers. So we'll regard every addition from 0 plus 0 equals 0 to 9 plus 9 equals 18 as taking one step. Now suppose we're adding an n-digit number and an m-digit number. If n is not equal to m, then sometimes we're adding 2 digits, and sometimes we're not. So sometimes a harder problem is easier to analyze. So we could make our analysis easier by assuming both addends have the same number of digits, introducing leading zeros if we need to. Now first we'll find the exact number of steps required, but then we'll use divide and conquer to find a bound. Since we're adding two n-digit numbers, we have to perform n single-digit additions. So t of n is n. Or is it? Remember, if you don't find your mistakes, someone else will, and no one ever complained when a job was completed ahead of schedule. In other words, we want to use a worst-case analysis. The biggest multi-digit numbers are those whose digits are all nines. So what if we add, say, 999 to 999? So we can add, and note that when we add, we often have to introduce a carry digit. So in the worst-case scenario, adding two 3-digit numbers requires one sum of two 1-digit numbers, taking one step and introducing a carry digit, and then there's two sums of three 1-digit numbers, taking 2 steps each, for a total of 5 steps. If we generalize this to two n-digit numbers, we'll have one sum of two 1-digit numbers, taking one step, n minus 1 sums of three 1-digit numbers, taking 2 steps each, for a total of 2n minus 1 steps. Now, let's consider this from a divide and conquer perspective. Suppose we add two k-digit numbers. Then adding two k plus 1-digit numbers can be accomplished by performing two more additions: the addition of the actual digits and this one extra addition of a carry digit. So t of k plus 1 is t of k plus 2, or letting n equals k plus 1 gives us the recurrence relation. So let's assume we have no insights into big O of t of n. So we'll start by assuming t of n is big O of n to the k for some k. In other words, we'll assume it's polynomial time and see where that takes us. So if Tn is big O of n to the k, then for any c and for all sufficiently large n, t of n is less than or equal to c n to the k. So that means t of n minus 1 is less than or equal to c times n minus 1 to the k. And we can substitute that into our recurrence relation. Now to proceed, remember that addition and subtraction are hard, multiplication is easier. This plus 2 is a little problematic. But since this is supposed to be true for any value of c, we can always use c greater than or equal to 2, so we can replace 2 with something greater. How about c? And this allows us to turn this addition into a product by factoring out the c. Now, to go one step further, remember, concrete never hurts. The problem here is if we can show that n minus 1 to the k plus 1 is less than or equal to n to the k, we're done. So suppose k is actually equal to 1. Then we have, and so our statement is actually true for k equal to 1, and so t of n is big O of n.